Everyone, welcome back to my YouTube channel. This is the video lecture on operational amplifiers, and in this video lecture series we'll be discussing about operational amplifier applications. Okay, in this first part, that is 3.1 that I call, we'll be discussing about ideal inverting and ideal and non-inverting amplifiers. So let us begin our discussion. The operational amplifiers can be used as an ideal inverting amplifier, or it can be used as ideal non-inverting amplifier as well. Okay. So first let us discuss the ideal inverting amplifier. The circuit diagram of our ideal inverting amplifier is shown over here, in which we'll be giving the input voltage Vin to the inverting terminal and non-inverting terminal is connected to ground. Fine. And there is a feedback path which is going from inverting terminal to the non-inverting, that is output terminal as well. Fine. See, on the input side we have resistance R1, and the output side we have resistance RF, that is connected in the feedback path, that is where the suffix EF is given. Fine. From the characteristics of ideal op-amp, we know that input impedance is very high. The input resistance or total impedance is very high. Hence, no current enters the op-amp. The meaning is, whatever the current that is flowing through the op-amp is zero. Meaning is, whatever current that is coming from the input side, that is I, all the current will be passing through this feedback path and it will be reaching the output side. Okay. Now, so in this ideal inverting amplifier, we make use of a very important concept called as virtual ground concept. Now, what is this virtual ground concept? By this concept of virtual ground, we say that two input terminals are always at the same potential. The meaning is, here we have, this is one input terminal, this is another input terminal, and call this as point A, at this as point B. What we say, what this virtual ground concept says is, potential at A is equal to potential at B. The meaning is, whatever voltage will be there at potential B, same voltage will be available at the point A. Now in this case over here, this non-inverting terminal, that is point B, is connected to ground, and ground will be always having zero potential. So VB is zero and VB is equal to VA. Hence what we can say from the virtual ground concept is, VA is also equal to zero. Also we can write as VA is equal to VB is equal to zero. And that is how that is what the virtual ground concept says. Now from this circuit diagram, let us try to write the expression for the current that is flowing in, that is I. Okay. Now how do we write this is, we consider the direction of flow of current that is flowing from left to right. So what we do is, first we will write down this voltage V in minus of this voltage VA divided by R1. That is what I written. I is equal to V in minus VA divided by R1. Now, but what the virtual ground concept says is VA is zero. So if I make VA zero, so this expression reduces to V in by R1. Let us call this as equation 14.1. Similarly, from the output side also, we write the expression for I. From the output side, we will be writing the expression for I. Here also current is flowing from left to right. So if you want current this, if you want to write the expression for this current I, what we have to do is, we have to take voltage at this point VA, voltage at this point, that is V naught, divided by RF, that we have to write. That is what is being written over here. I is equal to VA minus V naught divided by RF. Since VA is zero from the virtual ground concept, so we will be having I is equal to minus V naught by RF. Let us call this as equation 14.2. Now this expression 14.1 and 14.2 both are written for the same current I. So let us equate them together. That is, V in by R1 is equal to minus of V naught by RF. That is nothing but this 14.2. Now we will write the expression for voltage gain AV. Voltage gain AV is equal to output voltage by input voltage, which is equal to minus RF by R1. So how I got this expression is, from this we are modifying this expression. V naught by V in is equal to minus RF by R1. This is called as gain with feedback. Now, what is this minus sign signifying? This minus sign signifies the phase reversal. Okay, the meaning is, here in this diagram, like in this waveform, if this is the input voltage Vin and this will be the output voltage V naught. Fine, you can see the 180-degree phase shifting in the output side over here. So this is all about inverting amplifier. Next, let us go to the ideal and non-inverting amplifier. Okay. Now the circuit diagram of ideal non-inverting amplifier is over here. We have op amp, and here the input is given to the non-inverting terminal. That is point B. Okay. And inverting terminal is connected to ground through this resistors R1. Okay. Now here also we use the virtual ground concept. From the virtual ground concept, what I can say, potential at A is equal to potential at B. Fine. Potential at B is V in. Potential at A is equal to potential at B, and potential at B is V in. So from the virtual ground concept, what I can say is VA is equal to VB, which is equal to V in. Now let us write the expression for the current that is flowing at the output side over here. This current, let us write this expression for this I. Now current is flowing from right to left. So what we do is we have to take the output voltage V naught minus voltage at this point A, that is VA divided by RF. That is what is being written over here. I is equal to V naught minus VA divided by RF. Okay, since from the virtual ground concept, what we have is VA is equal to V in. So let us replace this VA by V in. So what we'll be having is I is equal to V naught minus V in divided by RF. Let us call this as 15.1. Now let us write the expression for I that is flowing at the inverting terminal. Here also current is flowing from right to left. So what we do is we'll take voltage at this point minus voltage at this point divided by this resistance, that is VA, and this point is connected to ground. So I take it as 0 divided by R1. That is what has been written over here. I is equal to VA minus 0 divided by R1. Since from the virtual ground concept, what we say, VA is nothing but V in. So we'll write it as V in by R1. Let us call this expression as 15.2. Now this both the expressions 15.1 and 15.2 are written for the current I. So let us equate them together. So on one side we have the 15.1, that is V naught minus V in divided by RF. On the other side we have V in by R1. Let us solve it a little. So let us split this LHS part. It will be V naught by RF minus of V in by RF, which is equal to V in by R1. Now this V in by RF, let us send it to the other side. It will become V in by RF plus V in by R1. Now what is the common over here? V in. So take it out. We'll be having 1 divided by RF plus 1 divided by R1. Now if you take LCM as R1 RFs, in the numerator we'll be having R1 plus RF. Basic mathematics you'll be knowing. Okay. Now our aim is to write the expression for voltage gain AV, which is nothing but V naught by V in. So what we'll do is V naught is there in the LHS, so V in is there in the RHS. Let us take this V in to LHS part and let us send this RF to the RHS part. Right? So we'll be having V naught by V in is equal to R1 RF divided by R1 RF, and this RF it is in denominator over here. If it goes to other side, it will become numerator. Now this numerator and denominator RF will cancel with each other. We'll be having R1 plus RF divided by R1. To split this up, we'll be having R1 by R1 plus R1 RF by R1. R1 by R1 will be giving you 1 and RF by R1 as it is over here. So final expression for voltage gain will be AV is equal to V naught by V in, which is equal to 1 plus RF by R1. We are not seeing any negative sign over here in the gain. The meaning is there is no phase inversion over here. Just see in the waveforms over here. If this is the input voltage V in, the output voltage is also in the same phase. There is no phase shifting. There is no phase change is happening. So that is what it is called as ideal non-inverting amplifier. This completes this part. Thank you.